Hello everyone, I welcome all of you for this IGBC AP Exam Preparation course. Myself Sarunan J. Bharati from Carbon Figure Academy. In this video, we will be talking about module number 11, Building Envelope and Passive Measures. So in case of energy consumption, if you take the contributories or consumption criteria, so industry consumes 46% as average, whereas agriculture holds 18% consumption and buildings holds 29% consumption. So out of that building, so it includes both residential and commercial. So out of these two options, the residential holds the major proportion as 69%, out of that buildings 29% contribution. So if you take a typical building, and within the building, what are all the different consumption areas where the electricity is being spent out? So we have different options: air conditioning, lighting, and ventilation, and other equipments, right? So out of which air conditioning holds the major proportion, 60%. So the next big thing is lighting. So if at all, if you want to conserve energy within your building, or if you want to practice some green aspects within your building, then these are the two major aspects that you have to focus: the air conditioning, which means HVAC, then lighting, right? So in this module, we will be talking about that air conditioning requirement, that is the humidity, which means so inside the building space there will be a requirement of the ventilation, continuous ventilation, because from the outdoor towards the indoor, lot of heat passage will be there, right? So how these things has to be measured, overcome, this particular module will be talking about that, right? So in this pie chart, the green, orange, yellow color one, we can able to see the envelope heat gain components. Here what they are indicating as envelope, the walls of the building, right? So what are all the heat gain components? So you can able to see wall conduction, glazing conduction, then internal gains, and roof conduction. So obviously in four sides we have wall, at the bottom we have floor, at the top we have roof. So from the floor nothing would come as some heat element. Only from the sideways and top ways we will encounter the heat ingress, right? So apart from out of these different options, which holds the major proportion? The wall conduction. Not the wall conduction, the glazing conduction. So holds 55%. And the next thing is internal gains. So internal gains, in the sense, it's all about from the electric lighting, computer and other electrical based equipments, and even from the occupants themselves, some heat passage and exchanges would be there, right? So if you want to focus on better in-house spaces, means then you have to focus on the glazing, right? Because from that glazing only 55% of outdoor heat is getting into your building space, right? So in this right side picture, you can understand within the closed envelope of a building room, what are the different routes where. So as shown in the right side picture, you can understand the various root causes of heat ingress from outdoor towards the indoor, right? So the wall conduction, the glazing conduction, and hot air infiltration sometimes, because the building envelope might be of different materials, right? So if it is completely concrete, then there is no infiltration possible. But apart from concrete, if you have some steel based or some curtain based and some wooden based envelope, means there is a little possibility of hot air infiltration might be there. So apart from that, only the conduction based ingress would be the major dominant entry, right? So what is meant by building envelope? So it refers to the physical barrier between the interior and the exterior environments of a building. It plays a crucial role in controlling the flow of heat, air, moisture, and light to maintain indoor comfort and energy efficiency. The envelope consists of several interconnected components, including roof, walls, that is external facades, then windows and glazing systems, doors, foundation and floors, insulation and vapor barriers. Right. So out of these six things that our interested components are the roof, walls, windows and glazings, and insulation and vapor barriers, because through these things majorly that the heat ingress would come into the space of building regularly. So these things needs the attention, right? So these are the different aspects where we can focus on the effective envelope design, so that to minimize the heat ingress and to ensure the better indoor comfort for the occupants. So what are the aspects? Orientation of the building, glazing system, then walling, roofing, and finally insulation. So insulation in the sense for both wall as well as roof, right? So let us see one by one. So in case of orientation, the orientation of a building plays a pivotal role in enhancing the performance of its envelope, directly impacting energy efficiency, indoor comfort, and environmental performance, right? So because orientation ultimately decides which side of the building receives maximum sunlight during the daytime, right? So a well-oriented building envelope maximizes the benefits of passive design by harnessing natural resources like sunlight, wind, and shading, right? So what are the different aspects into this orientation? Solar heat gain and daylight. So with respect to that aspect, in case of north and south direction is ideal for reducing heat gain and glare. So this is for exclusively for Indian conditions and Indian climate conditions. So north and south, that face, if you orient your buildings longer direction, longer side, so that would be ideal for reducing the heat gain and glare. So if you prefer east and west, that would be having high solar exposure, increases the cooling demand requiring shading as well, right? So it is like India is not some single climate region, we all know that. So we have multiple climate regions across our country. So depending on where the location is, accordingly you can look for more sun gain, or you can look for more or you can look for avoid the more sun gain, right? Right. So depending on the location. So north south orientation can reduce cooling loads by 15 to 30%. So these and all are some numbers, but we don't need to memorize it, or we don't need to fix with these kind of values, but it's just a typical reduction possibility with respect to orientation, right? Then wind patterns and ventilation. So when your building is aligned with southwest and northeast monsoon winds, for natural cooling, it will be better, right? Use courtyards and jallis, lattices, sometimes it is being mentioned, to enhance airflow. So courtyard in the sense, so from the top view of the building, if you just look down, you can able to see some openings, right? So that might be at the center of the building or some corner of the building. So wherever it is, so the outdoor air is having a huge entry to flow into your building spaces through that courtyard. So that courtyard having a courtyard and that respective kind of building design would be highly suggestible for increasing the natural ventilation. So that also the natural ventilation can have a potential to reduce your cooling demands by 20 to 25%, especially in tropical regions. Then shading and overhangs. So install deep overhangs on south facing facades for summer shading, and can use movable shading devices just like levers on east west sides to minimize glare. So this can be effective and can reduce solar heat gain by up to 60 to 80%. So shading and overhangs, again a very important aspect, can be crucial as well. So glazing and fenestration, so north south, so use large windows for natural daylight in north south, that uh, direction. So same way, if in the top the same north south is being preferred, so in that north south, if you prefer larger windows, then you can get the daylight without facing the sun directly onto your walls, right? So east west, use low E glass or double glazing to limit the heat ingress. So what is low E glass? So low emissivity glass. So it's a kind of a property of glazing system where it can reflect the sun rays back into the outdoor scenario, right? So it would only allow limited amount of heat gain into your building space. So it's a low emissivity and low higher emissivity will be applicable for different requirements, and depending on which side of the building holds that particular glazing, right? Accordingly you can prefer from low E and higher E glass, right? So low E glass can cut heat ingress by 30 to 40 percentage. Double glazing reduces cooling load up to 20 to 25 percentage, right? So these are up to orientation. Next we have the glazing, right? So before going into the glazing scenario, we should understand how the heat is getting conducted into the building through glazing, right? So there are three different modes of heat transfer is there, thermodynamics concept and all. So first one is conduction, second one is convection, third one is radiation. So for the visual understanding, you can take that picture as example. Conduction, transfer of heat through solid materials, that is conduction, right? In case of envelope design, how it plays a role? So use of insulation materials reduces conduction, lowering energy loss through walls, roof and windows. So physically you place something solid, between the walls, internal wall and external wall kind of there, so that you can reduce the conduction based heat transfer, right? Then convection, heat transfer through fluid movement, right? Proper ventilation design prevents heat buildup, improving indoor air quality and comfort. So you may think fluid movement, but here it is talking about ventilation. So fluid in the sense not only liquid, for air also they are treating in the same meaning, right? So convection, heat transfer through fluid, so you have to deal with more involvement of airflow, so that to manage or counteract the convection based heat transfer. Then radiation, heat transfer via electromagnetic waves, right? So for this particular heat ingress, we should use reflective surfaces or low E coatings on glass, so that to reduce heat gain through radiation, especially for facades exposed to sunlight, right? So now I hope you can understand how these different types of heat transfer plays a role in your envelope choices and designs, right? So in the right side, you can understand a typical glazing is there with with within the boundary of that glazing system, including the frame, the window frame and the glazing, how how and all the heat from the outdoor enters into the indoor building space, right? So on the left side is outdoor, obviously sun is there, and right side is the indoor. So the top one, absorbed solar radiation conducted through the frame, so it's a conduction. So because of this heating of the solid frame, some amount of heating is passing from outside to inside. That is the first thing. Second thing is directly coming in, directly transmitted solar radiation through the glazings. So the yellow color is radiation based, right? So that microwaves or electromagnetic waves, those kind of things. So normally we say infrared radiation, right? So that kind of radiation based heat transfer is happening directly through the window glass. From that proportion, some amount of radiated heat gain through the window is getting reflected back into the outdoor also. So it is reflected solar radiation. And because of continuous passing of this radiation through the glass, some amount of heat is staying inside the glass material itself. So that glazing absorbed solar radiant heat. So because of this continuous passage and reflection, the glass is solid, right? So it would have some absorption and conduction based gaining of heat. So that is what mentioned in that pink color downward arrow. It would stay there in the glass itself, right? And because of that glass holding heat energy, some amount of heat will be passed inward into the building and some amount of the heat will pass outward of the building, right? So as absorbed radiation, so it holds some heat gain, and both the sides it would dissipate in the form of radiation, right? Then heat conducted through the glass, right? So it is again the same thing would be happening, or in generic manner they are mentioning conducted through the glass through the frame, right? Then heat conducted through the frame. So what we can understand cumulatively is the bottom two is the ultimate heat gain routes, heat conducted through the glass and heat conducted through the frame. Because of these two different options or routes, these four are the different phenomena that are happening. So through the frame some amount of heat is coming. Because of the glazing, some ingress reflectance, holding back and further releasing of absorbed heat. So these are all the cumulative kind of mechanisms that let the heat flow through window glass from outside to the inside of the building. So within the context of glazing, these are all the different parameter we should understand, because while choosing the glazing system, these are all the values that they are going to play the role, right? So based on your requirement, you should be able to choose between high u value, low u value, high shading coefficient, low shading coefficient, so relative heat gain, solar heat gain coefficient. So these are the very important terms, right? So u value, it is measured in watt per meter square into Kelvin, right? So what's the definition says? The u value measures the rate of heat transfer through a material or assembly, right? It indicates how well a building element, it can be a wall, roof or window, resists the heat flow. So which means a lower u value means better insulation, right? So so you should understand like rate of heat transfer through a material or assembly. So low u value, low passing of heat into the building, which means better insulation. Higher u value, higher passing of heat energy into the building, so that is not a better insulation, that is a bad insulation. So low u value is good, higher u value is bad. So that way you can understand. So here in the typical examples, for a concrete wall, the u value is typically 1.8, whereas insulated wall, the value is reduced 0.2 to 0.6. So insulated wall, concrete wall, what is the difference? On the concrete wall, they are adding one more layer, physical solid layer as insulation. So it's a better resistance towards the heat passage. And same way, double glazing, you can see 2.0 to 2.8. So you should understand, complete blocked concrete wall has lesser number and glazing has bigger number. So just to keep the passage of heat, outside of the building, you can't, completely surround with the concrete wall, right? You need windows for whatsoever reasons. So you should understand glazing of one thickness, it has some amount of U value. Double glazing has a number of U value, and triple glazing sometimes people may choose, and depending on the thickness of the glazing also, the price of the glazing system would vary, right? Because double glazing means, so we will have a visual in the next slide. So I'm just letting you know, in between space of one glazing and another glazing, there might be empty space. Sometimes some gas filling also would be there. So according to what type of gas is being filled inside the, within the wall glazing, the cost of the glazing system would be differ, right? So how the calculation is, so U is equal to 1 by summation of R, right? Then the shading coefficient. So what's the definition? Shading coefficient is the ratio of solar heat gain through a specific glazing material to the solar heat gain through clear glass. So which has the SC of 1, which means shading coefficient of 1. So it measures the effectiveness of glazing in reducing heat gain. Again, a lower SC indicates better shading performance. So clear glass, it is 1. Tinted glass. So with respect to the clear glass, how effectively the little shaded tinted glass reduces the heat passage. Right? That is what the number says. So it is like SC is equal to SHGC. That is nothing but solar heat gain coefficient divided by 0.87. Right. So for tinted glass, it is reduced. For the reflective glass, it is completely reduced, 0.2 to 0.4 only. So you should have a lower SC value. Next, we have SHGC, that solar heat gain coefficient. It says the fraction of solar radiation that passes through a window and becomes heat inside the building. Lower SHGC values means less heat is transmitted indoors, improving thermal comfort. So again, the same way. So far the three different parameters, lower value seems to be better, right? So typical values for clear glass 0.85, low E glass 0.3 to 0.5, then reflective glass further reduced down 0.15 to 0.35. So how the calculation is done? SHGC is equal to direct solar transmission plus absorbed heat released inward. So in this picture, what we can understand, that yellow arrow component plus the right side red arrow component gives you the SHGC value, right? So then relative heat gain RHG, watt per meter square. So you can understand only U value has the unit, the shading coefficient and solar heat gain coefficient don't have the unit. It's just a factor, right? So what's the definition of relative heat gain? Watt per meter square. It measures the total heat gain through windows by combining solar radiation gain and conduction through glazing materials. So a lower RHG value indicates better performance for maintaining indoor comfort and reducing energy consumption. So again, it's the same way. U multiplied with delta T plus SHGC multiplied by solar radiation. So you don't need to worry about the formula. You don't need to worry about the values. You just need to understand the concept. Because in case of exam perspective, they would give you a scenario and they would ask, okay, in such condition, which type of shading coefficient you would prefer, low value, medium value or higher value. Just like that, this is how you should approach these concepts from the exam perspective, right? You don't need to memorize anything. what you need to do is you just need to understand the concepts, right? Then typical influence of these different parameters onto our envelope design. So in the right side what we have is that single glazing, double glazing and triple glazing, right? So this is how it would be. So inside that one glazing and another glazing, the empty space would be there, right? Sometimes completely vacuum will be there, and sometimes some purposely filled air gas also would be there, right? So U value, so lower U value improve insulation, reduce heat loss in winter and minimize heat gain in summer. So enhance the energy efficiency obviously. Then shading coefficient, again a lower AC reduces solar heat gain, particularly useful for windows exposed to east west sunlight, right? Then solar heat gain coefficient SHGC, lower SHGC minimizes low solar radiation ingress, helping maintain comfortable indoor temperatures and reducing the need for cooling. So ultimately telling, so what they are focusing on, that glazing part, so the heat conducted through the glass, so that component we have to assess with these different four parameters, and accordingly we have to choose the glazing material, right? Next we have walling. So what are the different options for walling? Concrete wall, brick masonry wall, insulated wall, that is cavity wall, then AAC block, precast panels, timber frame walls and green walls, right? So typically it might be listed based on a typical preference in some generic building construction, right? Concrete walls in case of large apartments and high story building, and in case of typical residential building or independent villa, these kind of where we use brick masonry and sometimes AAC blocks as well, right? So how these things are working towards the envelope and better energy efficiency into the inside the building. So concrete walls, high thermal mass stabilizes temperatures. So where these can be used to hard, dry or composite climates, these can be effective. What would be the drawback? High embodied carbon needs insulation. So high embodied carbon is one of the limitation, and in other sense we need some insulation is the other drawback, right? So typical U value. So okay, now can you able to understand? So this is how that U value will play a role in selecting the envelope material. So it could be a wall or glazing or anything, right? So if you would like to have better in indoor environment, then you have to ask about what is the U value, right? So it is typically 1.8 to 2 watt per meter square Kelvin, right? So then brick masonry walls, typical choice in Indian scenario. So moderate insulation but good thermal mass. It can be used effectively in hot, humid regions. So may require external insulation. So that is very much would be required. Even though we have some cement-based plaster, but still that won't be that much sufficient for arresting the heat ingress, right? Though, so their U value for brick materials, it is 1.6 to 1.9. So coming up with alternative brick products are there in the market. So what you should ask is whether they are satisfying the compressive strength requirement, because that is fundamental. Then you can ask about the U value. Okay, you are producing your brick with some alternative material or waste material, that is fine, good, congratulations, but what about the U value, right? So that is very much important. Then insulated or cavity walls in the sense it's simple brick masonry wall only, but it is constructed with some gap in between one wall thickness and another wall thickness, right? So that shows excellent insulation and soundproofing because there is a vacuum layer in between. So inside the that vacuum layer, empty space, you can fill some insulation material like cork or any wool or glass wool or whatever the wool material we have in the market as insulation, you can fill. But still, without filling any solid materials, if you just keep it as vacuum, that also would serve you a good and excellent insulation, right? So cold or temperate climates, these things can be preferred, and it would come with higher construction cost, because you should tell the people to keep the space throughout the external walls. So instead of following a typical fast manner wall erection, so here you have to keep it so slow, and you may need to lose some internal space as your external wall thickness will become somehow more. Okay, so that only they are telling higher construction cost. But the U value matters. It's drastically down comparing to the typical brick masonry walls. Same brick masonry, if you are following cavity wall system, can you able to see the difference between U value? It is 0.3 to 0.6. Then autoclaved aerated concrete blocks, AAC blocks, they are lightweight, high insulation. It can be useful for hot, dry, temperate climates. Requires surface finishing. That's fine, no issues, right? But it has almost equivalent to that cavity walls. So here, this is why that continuous innovation is required, right? So we just mentioned that because of providing cavity and achieving that good U value, you have to spend more amount in cavity wall construction, but the same U value you can achieve by using AAC blocks also. So now you should understand the difference between a typical cost comparison of a brick wall and a AAC block wall. Obviously, AAC block wall might be costlier comparatively, but what you should focus on, uh, you know, innovating uh, the production technology of AAC block so that it can be equalized with the typical brick masonry wall in terms of costing, right? So then precast panels, I don't know, prefabricated wall. So it can be used for fast construction, superior insulation, and urban and commercial buildings typically used. So limited design flexibility because of its fabricated scenario. So its typical U value is good, 0.5 to 0.8. So precast AIC blocks is almost like same. So AIC blocks in form of blocks, and precast, since it is made in factory, it might be following the same way of how AIC blocks are produced. So that only, or in terms of material composition, I'm telling, I'm not sure about how they are curing and all those things are happening. But still, because of the material composition, you could able to achieve the same amount of that U value. Then timber, good insulation, low embodied carbon, very importantly, useful for cold climates, sustainable projects. So if you visit any hilly regions for any vacation, you can able to see resorts are preferring these wooden materials in their interiors and major building components, right? Because of that, providing some anti-weather comfort from the outdoor in the indoor spaces. It's not suitable for humid areas. So that's also we should prefer. The timber cannot be used everywhere, right? Even though if you have affordability or availability, you can't prefer because of, so it may pose some negative indoor comfort issues, when you prefer for wrong regions, inappropriate regions. That's what humid areas, it should not be useful, right? So the U value, it's very good, 0.3 to 0.5. Then green walls, obviously, natural insulation improves air quality, all those things. Green walls are nothing but, I think we have already seen this one in our previous module, one of the previous module. Like growing up some vegetation as stacks onto your vertical walls, right? So it can be good for urban areas, hot climates, so requires regular maintenance. That's what very important here, but it provides some decent u value 0.6 to 0.8, right? So almost equal to precast panels. So these are the different options with respect to walls and indoor better environment. Next we have roofing. So with respect to roofing, concrete roof is the fundamental one we have. Then SRI based cool roof. SRI in the sense solar reflective index. Then high albedo roof. That also reflection based concept. So in the right side image, you can able to understand two different roof types are there. One is conventional roof paint absorbs heat, so almost 80 degrees Celsius. So inside of the building, it is almost 35 degrees Celsius. On the other side, if you are having that high albedo finish that has more potential to reflect heat back into the atmosphere. So the surface temperature only 50 degrees Celsius. So because of that, indoor temperature remains in 27 and 28 degrees Celsius range, right? So that is what that high albedo material based roof, that is reflective surface. And in the bottom, high SRI material based roof, right? So the black has SRI 0, so completely getting absorbed, and some light gray, that is solar reflective index, has 54, it is partially reflecting, and white, so it is more than 100, 108 SRI value, so it reflects almost everything that is being fallen on them. That's right. So concrete roof, it's a high thermal mass material, stabilizes temperature but may retain heat. So here I would like to clarify on what is mean by high thermal mass. So during the daytime, completely when the sun falls on the roof, the concrete will keep on receive that heat energy and would store them. When the sun goes off in the night, that absorbed heat will get dissipated slowly throughout the night period. That is thermal mass, right? Thermal mass. So it's a high thermal mass. It has a good capacity of absorbing, holding, then releasing. But if you take wood, it's not that much high thermal mass, but still it is better. So that is what they are indicating. So in your building, in walling or roofing, in which of the space of your interior spaces needs these kind of effects, so accordingly you can prefer the concrete or lightweight blocks or lower thermal mass material. So accordingly you can regulate the heat flows inside the different spaces of your building, right? So that's what I wanted to mention. Then concrete roof suitable for composite climates, needs insulation to prevent heat gain and all. Typical U values are there. Then SRI based cool roof uses high SRI material, better result. Then high albedo material, better result, right? So they are also having a typical lowered U values. So material examples, it is like for concrete roof, RCC with EPS insulation. For SRI based roof, white reflective paint, cool roof membrane, light colored tiles. High albedo, we have gravel, white marble chips, light color metal roofs, all those things. And finally, we have insulation, walls and roof. So we got, there are the different insulation options. EPS, expanded polystyrene, 0.3 to 0.5. XPS, extruded polystyrene, 0.2 to 0.4. That's a good. Mineral wool. Then PU foam, polyurethane foam, 0.2 to 0.3. Then cellulose insulation, it's a kind of thing susceptible to moisture because it's a kind of insulation, but it's not good against the moisture, right? Then reflective insulation, just like some layer or sticker or some tiles or paint, those kind of things, right? So this is how, in terms of roofing, different layers of material has to be placed. In terms of walling, again, in the outdoor or in the indoor, whichever the type of the insulation you prefer, accordingly you can install, right? So passive measures, they are the design strategies that optimize the building envelope's performance by harnessing natural elements such as sunlight, wind, thermal mass to regulate indoor temperatures and enhance comfort without relying on mechanical or energy consuming systems. So that is what the passive system, right? So in the right side picture you can see the wind tower. They are just constructed building element, but they are letting the outdoor air to pass through and flow through the wind tunnel and enter into your building, right? Same way, the earth air tunnel. So using these kind of technology also, you can cultivate or use the external air to cool your building's interior space. But these are the things has to be maintained and installed so properly with appropriate design guidelines and supervision, right? Yeah, or else it would be become a problem of moisture entry, odor entry, or insect entry into your buildings, right? So that's what the things are there, passive and active. So optimized orientation, shading, all these things are coming under passive. Active means you are installing additional material onto the building so as to regulate the heat and indoor environment. That is active, right? So passive measures, these are the different options: wind towers, geothermal, earth air tunnel, self shading, and buffer zones. So buffer zones are nothing but in providing some courtyards, right? So that open to sky zones would invite lot of amount of airflow into the building and would try to regulate the other space with respect to airflow and ventilation, right? That is a buffer zone. Self shading is nothing but, this is the self shading simple example: provide the some design elements onto the external wall so that the their shades or shadows are falling onto the wall of the same element, right? So that the walls will be under some self regulated shading, so it would reduce the heat ingress towards the building. Then earth air tunnel, that's what we have seen here. Then we have geothermal. Obviously geothermal, earth's stable underground temperature to heat or cool the building, right? Then wind towers, obviously this is what it means. So these wind towers are very simple to construct because these passive measures are to be designed while you are doing your design phase itself, right? Once the construction is done, you can't go for the passive measures so effectively. So before concluding your building design, the architectural firm or whatever it is, so you should incorporate this passive mindset so that you can do lot of goodness to your building without additional installations, additional castings, and all those things, right? That's why it is called the passive measures. It will be there, that's all, simply, but it will do its job. Then the next module we will see in the next video. So as I already mentioned, so please make use of the module wise quiz which is being provided in the description box. See you.